For this lesson, we're going to be revisiting a concept from the Advanced Functions course, which is rates of change. And in continuing with what we've done in the past lesson, we're going to be looking at it in the context of the idea of a limit. So first of all, just a very simple refresher. If we have a function f of x, then normally we are going to represent the independent variable as the x value, and whatever comes out of that function, the result, when I plug in my value for x, we normally assign that to be the dependent variable, that's y. So the rate of change, whenever we talk about rate of change, we're asking about how is the dependent variable changing with respect to the independent variable. So at its most fundamental level, rate of change is the change in y with respect to the change in x, which is just a slope. Now, when as we move forward, we become more interested in not in this slope between 2 points, but we are interested in the slope at a point. And that is known as the instantaneous rate of change, which is the same as the slope of a tangent line at that point. And so instead of just delta y over delta x, which is what f of a plus h minus f of a, that's your delta y, and we're setting our delta x to be some small value h. Now we want to consider the limiting case where that value of h approaches 0. Now there's another way that we can think about this, and I want you to understand that it is exactly the same as what we just talked about. It's just packaging it a little bit differently. So let's go back again to that same idea. Let's imagine we've got a curve and we want to know that is my x equals a. So that would be the point P. If I want to know the tangent slope, sorry, my wrist just moved there. If I want to know the slope of the tangent at this point, one thing I could do is I could take the point Q, which has an x-coordinate at equal to b, and then I could slide this q closer and closer to p. So for example, that would be my x1 at a, which would mean this would be my y1, that would be my x2, and this would be my y2. So f of b would be the y value of the second point minus f of a, the y value of the first point. This is just y2 minus y1 over x2 minus x1. This is the slope. And if we want to go from the slope of a secant to the slope of a tangent, what I have to do is bring these 2 points closer and closer together. So what that means is this interval has to approach 0. I have to make this smaller and smaller. Well, that's the same thing as taking this value of b and making it closer to a. And so that's what I'm saying here. It is the limit as the x-coordinate equal to b, as this value gets closer to this value. And if this value, if b is approaching a, then b minus a is approaching 0. And that is exactly the same as when we have h in the denominator and we say h approaches 0. Now it's generally convenient that we don't talk about it. This was fine for illustrating using a and b. But in general, we actually drop the b because we're going to take the independent variable and we're going to move it closer and closer to a anyway. So we generally, an alternate form, that's what we're talking about here, an alternate way of writing this is the instantaneous rate of change is the limit as x approaches a of f at x. Notice I had f of b here. Now I'm just going back to calling it f of x. Minus f of a, that stays the same. B minus a becomes x minus a. As is often the case, the best way to get your head wrapped around this is to illustrate it using an example. So we're going to do that now. We're going to do the same question. We're going to answer it 2 times. The first time we're going to use our standard definition, and our standard definition, so this is for part A. Our standard definition is that the instantaneous rate of change is equal to the limit as h approaches 0 of f of a plus h minus f of a all divided by h. Now we're going to have to modify this in order to put it into a form that makes sense for us. And I guess the other thing that I want to mention here, you're going to notice this in a little bit in this lesson, but you're going to notice it a lot in the textbook and in your homework and your assigned questions. They're going to start to make references to certain rates of change which they may not explain, and I'm going to explain at least this one, and then in class we'll talk about others. Velocity is defined as the instantaneous rate of change of position. Those of you who've done some physics are already familiar with that idea. So velocity, normally we use the symbol v here for velocity, and in our equation we've used the symbol s of t for position as a function of time. So first of all, we're going to take the limit as h approaches 0, but instead of f of a plus h, it's going to be s of something plus h, but instead of a, what I'm going to use is the value 1 second. So that's going to be s of 1 plus h minus s of a, but again, my a value is 1 second, divided by h. So that is equal to the limit as h approaches 0. Now, s of 1 plus h. Well, here is my function, 80 minus 5 times something squared. And the thing that goes in there is whatever was here, 1 plus h. Minus, bracket, again the function, 80 minus 5 times something squared. And in that case, in the second one, that's just going to be the 1 that goes in there. And that's all divided by h. The limit as h approaches 0, just a warning here, as I write this for the third time, some people find writing out the limit as h approaches 0 gets quite tedious, and either intentionally or unintentionally, sometimes this gets dropped and then it gets added in at the end, or even worse, it doesn't get added back in at all. Adding it back in at the end, that would be a pretty major communication error, or dropping it in the first place. But not adding it back in at all, that's an actual error. It's no longer mathematically correct. So please make sure that you keep this going. If it really bothers you, you can take some of your algebra and go do that to the side in rough work, and then bring in the result of your rough work with the limit, and then evaluate the limit. Now in this case, I'm going to go ahead and evaluate as part of the overall statement. So that is 80 minus 5, and then 1 plus h all squared is simply 1 plus 2h plus h squared, minus, and then in the other, sorry, I need another square bracket there, and in the other bracket, this is just going to be 80 minus 5 times 1 squared, which is just 80 minus 5, all divided by h. That is equal to the limit as h approaches 0. Now I've been keeping these brackets here. I didn't really need to keep this first set of square brackets, but the second set, just to remind me that that negative has to be multiplied into both, although I'm going to be able to simplify this so it won't really be an issue. I've got 80 minus 5, and again this negative 5 has to be multiplied into this entire bracket. So that's going to be minus 5 minus 10h minus 5h squared, and then over here I had 80 minus 5, which is 75, so that's just going to be minus 75, all divided by h. The limit as h approaches 0. And if you take a closer look, we've got 80 minus 5 here is 75, minus 75, that's just equal to 0. So all we have left in the numerator there is negative 10h minus 5h squared, all divided by h. And something that I've been trying to stress when we're taking these limits, one of the things we're looking for are opportunities to get rid of or divide out any of the values that are going to go to 0. In this case is h, that's in the denominator. So I actually have a common factor in the numerator of negative 5h, and that's multiplied by 2 plus h, all divided by h. And I did get that opportunity to divide out those h's. They become 1's instead. That is equal to the limit as h approaches 0. And I'm just going to write it out one last time. Negative 5 times 2 plus h. This is fine the way it is, but I don't think the form looks very good. So I would recommend adding a bracket here to denote that I'm taking the limit of this whole thing inside the bracket. And when h approaches 0, that means that this value of h approaches 0. Sometimes we do this in math. We draw a line with an arrow through that individual value to say this is going to turn into 0. And so all that is going to leave me is a negative 5 times a positive 2. And now I've actually evaluated the limit, and that is equal to negative 10. Now, when you're doing these questions on rate of change, I want you to be particularly careful. Once you've figured out what we're talking about here, for in this case, velocity is the instantaneous rate of change of position, don't forget your units. So what we have is position. These are units of meters over the time, per unit time. So this is therefore the velocity after 1 second is negative 10 meters per second. Now, for those of you with a bit of a physics background, you might not care for that entirely, and I'm going to talk about that in a little bit. But for now, you also have this option. You could have also said 10 meters per second down, with the understanding that this negative 10 actually means that it's down. Or you could have even said negative 10 meters per second up. And that's really closer to what I was saying with the original statement. So I'll talk about that shortly. For now, though, let's go on and do part B, which is we're going to use this alternate method. And again, just to remind you of this alternate method, or this alternate representation, it is the limit as x approaches a of f of x minus f of a, all divided by x minus a. Now we have to adapt our current situation. So we're talking about velocity, which is going to be the limit. Now our independent variable is not x anymore. Our independent variable is t. So it is the limit as t approaches. Our value for a, well, we don't want to leave just a value for a. That's actually going to be 1. We're going to replace that with 1. So it is the limit as t approaches 1 of, and one last change, I won't change the color for this one, it's going to be s of t minus s of 1, all divided by t minus 1. So that becomes the limit as t approaches 1. Now s of t is just the original expression, so it's 80 minus 5t squared. Once again, I'm just going to use brackets to isolate these as I fill them out. S of 1 is 80 minus 5 times 1 squared, all divided by t minus 1. That is equal to the limit as t approaches 1. This first bracket was actually unnecessary because it's a positive 1 in front, so I'm just going to go ahead and write that as 80 minus 5t squared. Minus, now this bracket, we can evaluate this in one step. 5 times 1 squared is just 5, so this is 80 minus 5, which is minus 75, over t minus 1. So that's going to simplify in the numerator. The limit as t approaches 1, 80 minus 75 is simply equal to 5 minus 5t squared over t minus 1. I can't evaluate this limit as it stands. As t approaches 1, 1 minus 1 approaches 0. I get division by 0, and that's not going to be useful. So I need to figure out another way to simplify this. And something you might recognize here is if I take out a common factor, there's a common factor here quite visible as 5. It depends on how you wrote this, but you know what? I'm just going to go ahead and write it the way it's written and show you that you should still be able to see it and adapt to it. Now when I see this, I have 5 times 1 minus t squared. Normally we have the quadratic term first. Normally we make the quadratic term positive. I could have factored it that way, or I could have written this as the limit as t approaches 1, and I could have said this is negative 5t squared plus 5 over t minus 1, and that's equal to the limit as t approaches 1 of, and I'm going to take out the negative 5 this time, and I end up with t squared minus 1 over t minus 1. Now I'll finish with this right side because I actually think it's the easier one. The limit as t approaches 1 of negative 5, t squared minus 1 is a difference of squares. That's t minus 1 and t plus 1, all divided by t minus 1. And then you recognize that t minus 1 divides out with t minus 1, and we just end up with the limit as t approaches, not negative 1, positive 1. And this is going to be of negative 5 times t plus 1. And I'm not going to evaluate that limit yet. I just want you to see that we end up at the same place here. The limit as t approaches 1 of 5. Now this again, this is still a difference of squares regardless of the ordering of the terms. This difference of squares though is 1 minus t times 1 plus t. And this is a mistake I see students making, which is they know they want something that has t minus 1 in it, and so they just force it and they make one of these terms t minus 1 so they get that nice division. But that's not how it works. You have to be, obviously you have to correctly do the mathematics as it's presented to you, or if you're not comfortable with that, you can rearrange things so that it works out being in a form that you're very familiar and very comfortable with. But I just want you to understand that this is not so terrible the way it's written right now, because I take a look and I say, okay, well 1 minus t and t minus 1 are very similar. If t minus 1 goes into itself once, how many times does it go into 1 minus t? And it turns out it goes into 1 minus t negative 1 times. And so we just end up with the limit as t approaches 1. 5 times negative 1 is equal to negative 5. And 1 plus t, well, 1 plus t is the same as the t plus 1 we had over here. And again, I'm going to put a bracket around that to make it a little bit clearer. And then both of those end up coming together to give me the same result. As t approaches 1, 1 plus 1 is 2. Negative 5 times 2 is equal to negative 10. And that works for either side because these are now identical to each other. And so from there, I get my same therefore statement as before, negative 10 meters per second. Okay, that's it for this example. I just want to make a quick comment about the physics. And it's the kind of thing that, as a physicist, it's the kind of thing that I see in math textbooks, for example, and I don't think it's handled terribly well. And so just a very quick note to this, whether you have a physics background or not, if you have the physics background, you probably see some of the same problems with it that I do. And the problem with it is the idea of a vector having magnitude and direction. And this concept is something we're going to be covering in this course regardless of whether or not you've seen it in physics before. Now, one way that we can explain around this, particularly because it's fairly widespread to see this in mathematics books, is if you're dealing with, particularly with one-dimensional problems where it's just something like, for example, up or down, left or right, If we can define a particular direction as positive, so in this case we defined up as positive, the idea of direction is being incorporated into our expression. And that the way that's incorporated is a positive number would represent up in this case, a negative number would represent down. As far as the vector symbols go, sometimes, just for the sake of convenience, it's like what I was saying about writing out those limit statements all the time. It can get a bit tedious, and there are times where you can certainly make the case where if you have constrained your situation so that there's no room for misinterpretation, for example, if all you're dealing with is up and down, and you've defined positive being up, at that point in time, it's understood that direction is included in the sign here, whether it's positive or negative. And so for the sake of convenience, it is acceptable to drop that vector symbol. Now, as soon as you're dealing with 2 dimensions again, that sort of thing, you have to go back to using the vector symbol. There's no other way. I'm not crazy about this as an explanation, but it's an okay rationale to use, and we need to use it so that we can not go crazy as we see how these things are represented in the majority of math textbooks, at least at the high school level. Okay, that is it. So doing rate of change, this is not a new topic, so some things, just something I want you to keep in mind when you're doing your rate of change exercises is units. Make sure that you take a really careful look at the units of the problem. What are the correct units for the rate of change? And what does the rate of change actually represent? What does it mean? And then the other thing you might want to keep in mind is vectors. And this is going to be more or less comfortable for some of you. The idea of what are the positives and negatives meaning if there is any direction involved in the work that you're doing. Okay, that's it for this one. Like I said, rate of change, this is review. But the idea of taking a limit is definitely an important concept and one that we're going to continue to leverage as we go forward in this unit.